All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. We're moving through Unit 6 here on thermochemistry and thermodynamics. And now we're going to take the information that we've learned about how we can quantify energy changes. We looked at calorimeters, we looked at energy of phase changes. Now we're going to start to apply this to chemical reactions. Now remember, when we first introduced enthalpy, we said that delta H could be the heat of the reaction or the enthalpy of the reaction. And so we're going to introduce that. We're going to look at how that can be represented within a chemical reaction or a thermochemical equation, and we'll actually look at how do we solve them. Now this is going to correspond to section 5.4 in the Brown and LeMay textbook that we're using, so please make sure you go and read through that, check over that. That'll give you a good insight as to what we're going to be looking at. So let's dive right in here. So enthalpies of reactions, or heat of reaction, or delta H reaction, right, is what we're referring to. And it can be represented in one of two different ways. And in both of these, right here, these are both known as, these are thermochemical equations, right? They're thermochemical equations because they show us or they tell us something about the energy that's being transferred. We've got, it's the same reaction, but they represent it two different ways. The first one, you've got 2H2 plus O2 produces 2H2O, and then it tells you directly after it that delta H is negative 483.6 kilojoules. Now that negative is letting us know that it's released, telling us that energy is a product. Now, the other way that it can be represented is we've got the 2H2 plus the O2 makes 2H2O. But then look, they've written plus 483.6 kilojoules because, again, energy can't have a negative value. It's just simply telling us the direction it's moving in. So writing plus 483.6 kilojoules here as a product is letting us know, okay, energy was released here. Now, like I was saying, in both of those processes, it's indicating the reaction's exothermic. And this reaction is showing us the amount of heat released during the reaction as it's released. So if there are 2 moles of H2 that's consumed, if there's 1 mole of oxygen that's consumed, or if there's 2 moles of water that's produced, like if all those things happen, then that's the amount of energy that's going to be released by that process. Okay. And the good news is let's say we had more than what we have there. Then what we can do is we can use the mole ratio within our thermochemical equation to treat this like a stoichiometry problem, right? And so we could just simply do a mole calculation, and then we can determine what's the amount of energy that's being released. Now, remember, delta H of the system is going to be equal to Q at constant pressure. Right? So that's essentially what we're doing because we're assuming, like in most chemical processes, that pressure is staying the same during our chemical process. Now let's look at a different example. So we got the same reaction, we get the delta H, and we want to know how much heat is associated with the reaction of 3.6 moles of hydrogen gas with excess oxygen. All right, so here they're telling us we got plenty of oxygen, but instead of 2 moles of hydrogen reacting, we're going to have 3.6 moles, right? And so here's what we're going to do. We're going to say, okay, I know that from this particular process that we got 3.6 moles of H2 is what I've got. And based on my thermochemical equation, this reaction's telling me that for every 2 moles of hydrogen that's consumed, and we get that from right here, for every 2 moles of hydrogen that's consumed, that it's going to release 483.6 kilojoules of heat, right? And so we got 3.6 times 483.6 divided by 2. So in that particular case, that means that we're going to have approximately 870 kilojoules of heat, released, right? And that should make sense. The number should be larger. We had 3.6 moles rather than 2, so it should be larger than the 483.6. It's not quite twice because we only have 3.6 moles, not 4. And so we get an increase in energy. The total energy released would be 870 kilojoules based on that particular process. All right. All right, and this is a fun one right here. So it says if 45 kilojoules of heat are absorbed by a sample of water, how many liters of oxygen gas would be produced at 1 atmosphere and 298 Kelvin? Oh man, this is a lot of fun, right? So it tells us that water absorbed 45 kilojoules of heat, right? And so essentially, what we're saying is 45 kilojoules of energy was absorbed by the water. So we know if we were going to decompose this, essentially we flipped the reaction. So we're saying, all right, 45 kilojoules is what I'm starting with. And I know from this reaction that for every 2 moles, or there's, the amount of energy that's absorbed here that this corresponds to is that there's 483.6 kilojoules of heat that needs to be absorbed to help break down 2 moles of H2O, right? All right, so then we know, okay, and then for every 2 moles of H2O, we've got 1 mole of oxygen that would be produced. So we got 45 times 2 divided by 483.6 times 2. And so from this particular process, we've got 0.0931 moles of O2 that's produced. Now again, they want liters of oxygen. I've gone ahead and set this up as if it's a ideal gas problem. So we've got this mole, so now we've got PV equals nRT. Now we can find V. So V is going to equal to, what is that? nRT over P. So our moles, 0.0931 times 0.08206 times 298 all over 1 atmosphere. So times 0.08206, that's our ideal gas constant, times 298 divided by 1. And then that's going to be 2.28 liters of O2. Okay, I'm trying to think, I'm looking at this just to make sure. I think we can also just do the stoichiometry. We can say, all right, that's how many moles times 22.4. No, that's probably better. Go ahead and use the ideal gas equation here. So use the ideal gas equation, you get 2.28 liters of oxygen that's produced. And that, ladies and gentlemen, that's how you do bond enthalpy. It's not complicated. Or reaction enthalpy, you just simply take the information that's provided. You got more or less moles. You do a simple stoichiometry. So it's essentially stoichiometry with thermochemistry. All right. So thank you guys for joining me. Thank you for watching this. I hope it was insightful. If you do have any questions, please don't hesitate to reach out to me. You know where to find me. Thank you guys so much. I'll see you guys again soon. Take care.